Welcome to Phenomenal Science Teaching with Dr. Vic Sampson, and today we're going to be focusing on phenomenon in science education. The reason we want to talk about that is the idea that we've adopted new standards, which we call TEKS in Texas, that are three-dimensional in nature. And we've talked a little bit about this in past webinars. But if you think about the three-dimensional focus of these new standards, it's trying to align with the three dimensions of science, doing what it means to do science, right? So you have these science and engineering practices, you have this disciplinary content, you have these recurring themes and concepts. And if you focus on all three of those at the same time, that becomes a three-dimensional approach to science education. So it's not just enough to focus on content or processes or just themes. It's really, the goal is to focus on all three of these at once. Now, since the TEKS are now three-dimensional, and as well as other standards in the US that are being used, such as the next generation science standards, there's also an expectation for instruction to be three-dimensional as well. So if you relook at that graphic again, and you start thinking about those three parts of science, the practices, content, recurring themes, if you ask students to engage in one of those or learn about one of those at a time separately, that's kind of a one-dimensional approach. If you focus on two of them, say focusing on practices and content, that is a two-dimensional approach. But if you have kids using content, a framework, and multiple practices to figure out a phenomenon, then you have three-dimensional instruction. And this is really where we're moving toward in Texas and across the United States, of giving kids opportunities to use these three dimensions to figure out phenomenon. So since that's such a focus, many of you may be wondering, well, why phenomenon? Like, why is that important? What does that do for us to focus on phenomenon inside a classroom? Can't we just focus on the three dimensions? And where the basis of this comes from is the National Academies, who published the framework for K-12 science education in 2012, and which really serves as the foundation for the new TEKS that have been adopted in Texas, as well as the NGSS. Really comes down to this quote. I think it's a nice way of thinking about this. So, engaging students with standard scientific explanations of the world, helping them to gain an understanding of the major ideas that science has developed, is a central aspect of science education. Asking students to demonstrate their own understanding of the implications of an idea by developing their own explanations of phenomenon, whether based on observations they have made or models they have developed, engages in an essential part of the process by which conceptual change can occur. So if you think of conceptual change as learning, changing your ideas about how the world works and making sense of that, it's important for kids not only to know these explanations that science have developed, but also then using the same ideas and the themes and the practices to develop their own explanations of new phenomena that haven't been introduced to them yet. And by engaging that process, that helps them actually adopt these ideas and use them as their own and see how useful that they can be. So it's a really powerful way of thinking about helping kids learn in science. So if that's the why, it's important to really understand, what do we mean by phenomenon, right? So what counts, what doesn't count? How is this idea different than maybe how we've been thinking about it in the past? So what I want to do start off is give you a quick definition, and this is the one I tend to use. It's just an observable event that happens in the world around us, something we can see happening. And the important next part of that is there's some underlying explanation for that phenomenon, and what we need to do is then figure out what is that explanation, or what's causing it, or why or how those things happen. So let me give you a few examples of what that looks like. Here's a quick video to watch to check this thing out. Now, we would call this, I would consider this an example of a phenomenon that we can use in science education, because it's an event that happened, something that we see. It's definitely real world, and it automatically has an underlying explanation that many kids would find interesting and want to know about. Why is this happening? Why do we see the hail? Why is it so large, right? It has those kind of three components. Here's another example of a good phenomenon. So once again, event, real world, and many of us are already going, why is that happening, right? So once you have all those three parts, great phenomena used in science education. One more example from life sciences. Litter of puppies, different traits, right? It's an event, definitely real world, and requires an explanation. Well, why do they all look different if they're siblings and come from the same parents, right? So you have those three components. Now let's contrast those with things that might on their surface look like phenomenon, but really don't meet these three elements. So here's the first one. This is a common thing that's done in biology classrooms or life science classrooms often, is kind of the genetics of aliens, right? So they'll be supplied with a set of rules for how the traits of aliens are inherited, and then they have to figure out what producing offspring from these two parents would end up looking like. Now, so thinking about this, is it an event? Yeah, so you can say there's something happened, there's offspring being produced. Is it real world? No, because it's a made up situation. And the explanation's not really there because they're applying rules to show that they don't understand the inheritance that was presented to them before, right? So there's not really anything to figure out in that piece. Here's another one, common for physics, right? So we'll use an example of a parachuter and then asking kids to calculate the parachuter's coefficient of drag before deploying and after deploying the parachute, right? So in this case, we don't have an event. This is a hypothetical situation. It is real world. That's often used as this connection to, hey, there are parachuters and this is something that happens. Are they figuring out an explanation for why the parachuter slows down? Not really. They're being told how to use mathematics to calculate something, right? So there's not really this idea of explaining the underlying of why or how something happens. Here's a couple more examples. So we'll often show pictures of organelles in life science, parts of cells. Is that a phenomenon? And once again, we don't really have an event because nothing's really happening here. These are illustrations or images of things that are found inside our body. So it definitely it's real world, but we don't really go into explanation of why they're there, why some cells have these, why don't. It's more of a here's an example of what these look like in real life. Another example for you, a roller coaster. So in this case, it's a simulation of a roller coaster to illustrate the ideas of potential and kinetic energy. Is this a phenomenon? And once again, if you look at those three criteria, event, sure. So we can talk about a roller coaster going. Is it real world? Not in this case, right? It's a simulation. It's designed to mimic the real world, but it's not really the real world. And is there an explanation for why the kids developing an explanation of why the roller coaster moves over time or how our energy changes? No, it's used to illustrate a concept that they are learning about, right? So it doesn't really count as a phenomenon again. I'm going to give you two more examples here. This one's pretty common, something like this. It's showing a picture of, say, a playground and then saying something like, hey, name all the forces in this picture. Is that a phenomenon? And once again, you go through the three things. Is there an event? Yep. Right? So there's something happening. It's definitely real world, but we're not explaining how the movement of the kid on the swing. We're using this as a context to describe vocabulary, right? Or apply vocabulary. So could be very useful, just not a phenomenon, more of an application. And then the final one is maybe we have some kind of model that looks like this, right, of the water cycle that explains how water moves on Earth. Is it an event? No, because it's not something we're observing happening. We're seeing the model itself. Real world, once again, is a simplification of things that are happening, right? So this is the explanation of what's happening on there. So this is a way to share an explanation of something that's happening in the real world event, but it's not the real world event that's actually happening. So hopefully that kind of helps clarify what is and what's not a phenomenon in science education. The last thing I want to talk about here in the time we have together is thinking about how we use phenomena in our classroom also changes the nature of instruction and what students will take away from a learning experience, right? So once you start thinking about these pieces of using these, how you go about using it matters. So here's kind of some advice I've got for you. So you can think of using phenomena in two ways. One, you can think of it using as making science cool or flashy, or you can think of it as sparking curiosity by introducing something to figure out. So let me give you an example of what that looks like. So here's an example of kind of making science flashy. So in that case, definitely something cool and flashy, definitely counts as a phenomenon. It could be something to explain, but it ends up becoming just kind of a demonstration of something cool. And you can see here kids saying, oh, that's awesome, right? But not really using a phenomenon in a way that sparks curiosity for something to figure out, right? Because we kind of end there, or we go about telling the explanation for how that's happening as it is, versus doing something like this. So in this case, then we see the mass of the steel wool changing and increasing, right? When it's sparked and catches on fire. Why is that, right? So if we organize a phenomenon, let's show this, and then tell me why that's happening. That gives the more of the idea of what will happen to of using phenomena as a way to spark curiosity, right? So I would recommend using it as a way to spark curiosity rather than abusing it to make science cool or flashy. Another way that has often been used is kind of to hook students before giving them an explanation. It's related much in the same way to the cool or flashy part versus creating a meaningful end goal of a learning experience. And let me show you what I mean by that. So here's the first one.
Classes are getting ready to start soon, and I've been working on some new demonstrations for my students. This one involves the generation of 3 different gases, and I'll bet you can guess why the last one's my favorite. Let me explain exactly what I just did. And here there was baking soda, which I added vinegar, producing carbon dioxide gas, which extinguishes the flame. Over here I've got potassium iodide, which reacts with peroxide, generating oxygen gas and causing the glowing splint to reignite. Over here we've got zinc metal reacting with hydrochloric acid, making bubbles of flammable hydrogen gas. Share this with somebody who needs a little science in their life.
So in that case, cool phenomenon of seeing what's happening in the video, but it goes on to explain everything that's there, right? So kids don't have an opportunity to figure something out versus organize something like this. Then you can introduce the idea of why do the cans of Diet Coke float and the can of Coke sinks, right? And it's intentionally designed to give something for kids to figure out by missing pieces, right? So there's other cans that weren't tested. There's some information about the mass of the cans. All of these kinds of things are designed to trigger wonder, right? So it gives you a meaningful end goal when you trigger that wonder, and then kids have to develop an explanation for that, right? So your goal then is to design, carry out an investigation about this. So you know that the lesson was successful when you can actually explain that versus being able to retell the explanation that somebody else gave you. Another example of that is giving a real world example of a concept versus giving students a reason to use the content, those recurring themes in the practices of science, right? So if you think about this is very common. We'll say something like this in biology where we're teaching about predator-prey population size relationships, and we'll say, here's an example of this concept. In Canada, we had snowshoe hares and lynx over time. Look, this is a real world example of this bigger concept. Versus having kids look at something like, say, this, and asking them to maybe develop a cause and effect question that they can use to explain why the water is coming out over time, or what causes the water to come out of the bottle, or thinking about measurement scales, or how would you measure the amount of water, or stability and change. It gives kids reasons to not only use practices and recurring themes and content and concepts, but gives them a reason to put them all together as a way to make sense of something new. So it's a great way to encourage kind of those three-dimensional pieces. Another way you can use phenomena that's really common is helping to explain a concept or teach terminology versus using it to support ongoing changes in student thinking. So let me give you an example of what that might look like. So here's a picture of this. Kind of funny line on the magnets, but you can say, here's a picture of magnets. Notice how they are attracted to the refrigerator. What do you think is in the refrigerator? What do you think the refrigerator is made of to allow the magnets to attract? Would the magnets attract to everything? So you use this to kind of explain or define terminology like forces or non-contact forces and pieces like that, versus showing them a magnet, something to do with magnetism, something like this. So students may come to this kind of scenario knowing about magnets attracting or repelling, right? But then they all of a sudden notice something that's odd, right? In this case, the distance between the magnets changing as you stack them on top of each other. Well, why is that? What's going on there? It gives them opportunity to start furthering their understanding of what's going on and using those ideas to support changes in the way they're thinking about the world around them, or these ideas that we've taught them in school. The last one is to kind of really think about using phenomena as giving students a chance to apply what they've already learned, or giving them an opportunity to use their own ideas as a starting point of figuring something out. Let me give you an example of what that might look like. So I've taught chemistry for a number of years. This was a classic one after teaching kids about the mole and stoichiometry. You give them some baggies and say, hey, here are bags of different powders. Right, they're just labeled with a number and a letter. You have to tell me what the identity of this based on how many moles are in there, right? So it's a great application problem, right? And they're using those ideas, but it's more of an endpoint, right, of that, versus saying, hey, watch this. Why do you think that happened, right? What's going on inside that tanker truck that you would get that to smush like that? Show you it again. Draw me a picture. Why is that happening, right? So you can use this phenomenon to open up these ideas of what's going on and what's happening to get kids more opportunities to spark their own ideas and then build on those other pieces of the core ideas and recurring concepts and practices throughout this. So interesting way to think about this, right? So what I usually recommend is trying to move more to the right side of this table versus the left. Now, there's nothing wrong with using phenomena for doing any of these things on the left side. But if you're interested in doing more three-dimensional instruction and really using phenomena as a lever to help kids learn, start moving it to the right side. Use it to spark curiosity, create an end goal for learning. give students a reason to use the 3 dimensions, support their changes, ongoing thinking, and give students opportunities to use their own ideas as a starting point and do some really powerful stuff in the classroom. Fantastic. So we just did our phenomena in science education today. Next week, we'll be talking more about 3D instruction, right? So what does that look like? How do you make that happen? What are the elements? What kinds of things you can do? Here's some examples of what that looks like in practice. So we're going to talk about that on the 15th. Then we'll also talk about on the week after that, which is the 22nd, we'll talk about 3D assessments in science education. So how can you assess students' use of core idea or of disciplinary content, recurring themes and practices at the same time versus kind of more focusing on either just content or vocabulary. Then we'll talk about how do you introduce a phenomenon so it creates a need. So once we've talked about what counts as phenomenon, but then how do we go about introducing that in class to maximize kids wanting to learn? We'll do that on the 29th. On the 7th of March, we'll talk about fostering learning after introducing a phenomenon. So what goes on during 3D instruction and what you can do to support learning. Then we'll spend 2 sessions talking about promoting and supporting student talk. And then we'll finally end of March with supporting how you go about supporting emerging multilingual learners in science when teaching in this manner. So hopefully you can join us. If they're 4 to 4:30 on Thursdays, remember to register at argumentdriveninquiry.com webcasts. If you do that, you can't make it, we will post we will send you a copy of a recording so you can still watch and take some nuggets from these, we hope. Also, if you're interested in any of our other professional learning that we do, we are often hosting events that are in person that are a little bit longer than these webinars. If you're interested in seeing any of those, you can go to our website and look at under programs and events. Or you can look at, there's a calendar there, or you can do look at more of our professional learning page at Argument-Driven Inquiry / professional learning. Thank you so much for joining me. If you have any questions about anything we talked about here today, you can reach me at victor@argumentdriveninquiry.com. You can also follow us on Instagram, Facebook, old Twitter, now X, at any of these handles. There's lots of people that are looking at stuff, and we try to post new content that is helpful all the time. So thanks so much for joining us for Phenomenal Science Teaching, and I hope you have a great afternoon.